Okay, so we want to continue talking about out-of-order execution. So we kind of like pass the first quiz. I'm sure that your TAs will discuss the solution with the quiz. If you have questions, reach out to us. Uh, in terms of grading, I think homework 1 and 2 should be out soon, and we will start grading your quiz also right away. That might take a few weeks, probably a couple of weeks. Plan is try to release it before the next quiz. Uh, but yeah, how do you feel about the quiz? So good, bad? Yeah. I mean, one thing about the quiz was, it was, time constraint in some sense, but part of it was intentional because I feel like it's useful to have that skill set of trying to be productive and trying to be accurate in short amount of time when you are time pressured, because you will see that a lot when you going into the wild, into working in some company or through your career as graduate students or PhD students and so on. So I think the fact that you become more effective when you have very limited amount of time, I think it's one good skill set that, in addition to knowing about processors and this designs and all those things, that I think another skill set that I want you to learn, and hopefully other people also do that the same for you in your exams. So that kind of once you graduate, you have that. Uh, uh, the plan is to want you to learn something from your quiz as well, and not just as a checkpoint that, oh, you did this. But grading should be, usually we give lots of partial credit. We give you bonus points and so on. So I wouldn't be too much worried about my grade if I were you, especially if you do the math, if you around 70 something on your quizzes, you probably get an A, because others, assuming that your projects and your homeworks and so on is good, and you get full grade on those. So I think majority of you will be, as I said at the beginning of the class, will get a really, really good grade. Any question about that? Any comments? All right. So I released a video about out-of-order execution. I checked the YouTube views, and it was pretty decent. So I think majority of you have seen it. So the idea that very briefly, I'm going to just go through that video. But if you haven't watched it, go and watch it. I'm not going to fully review it. But kind of where we were before the out-of-order was, we said that we're going to have a superscalar processor with multiple lanes, with forwarding, with branch prediction, with raw data hazards and all those things. And that was kind of what we get so far. Then we said that generally the problem with superscalar is that we cannot feed and utilize my superscalar all the time, just because of the hazards and dependencies. Compiler could help, but not the best way possible. So what we can do instead is the idea of out-of-order execution, which essentially we say that, okay, don't just limit yourself into small window of instruction. Just look at huge, very large window of instruction, and then try to find those that we call ready or available. And we're going to discuss what is available in this lecture. And then just feed those into your pipeline. And then if you have enough of those all the time, which in fact you do, then you can utilize all your pipeline, whatever number of superscalar lanes that you have, and then you will get n times faster processor, right? So that's the idea of out-of-order. Of course, there will be lots of questions that how do we do that? And we essentially said three things that we kind of need to fix. There are also some minor things that we need to fix that we might actually, if you have time, we might talk about next lecture. But the three main things that we kind of need to fix compared to our in-order processor is we need a mechanism for tracking instruction, basically knowing that which instruction is available, which one can go inside our pipeline. So that's one thing we need to fix. The second thing is that we need a mechanism for all those hazards that we talked about, for raw data hazard, control hazards, and so on. And as you will see in this lecture, there will be new type of hazards, unfortunately, because of the out-of-order execution. And finally, we need a mechanism for recovery, because if you do a speculation, and as you will see, we actually add more speculation to our kind of like, tool set. We need a mechanism to kind of like, go back and fix this issue. And that was the parts that we kind of like cover in the video. Basically what we're gonna get is this kind of like a machine, which essentially we read instructions still in order, but when we comes to the execution part of those instructions, we just pick those that are kind of available. So still there is kind of like a front end machine that's kind of like, still deal with the instruction memory and reads instruction one by one. But then we kind of decouple this front end from our back end, and like, in between put some form of a queue that I'm going to talk about. And then basically say, okay, whatever you read, go and put it there. I'm going to go through this list, and then I'm going to pick those that are available. I'm going to feed it into my machine for executing them. And then once they're done, because of the recovery issues that we talked about, I'm going to put them back in order. So I'm going to put them kind of like, back to the locations that we were before using another queue, or in some cases, these two queues could be the same thing. And then you can basically just, retire them in order, and then fix the issues that we face in our system. Okay, so that's basically our out of order mechanisms that typically all these modern processors these days are using. Essentially, the out of order part is really this part. The rest is still kind of in order. Okay, so when you're saying out of order, it doesn't mean that we are doing everything out of order. There's still lots of parts that are actually done in order. Okay, so we talked about the pipeline recovery, and the main thing that we talked about is comparing the out of order with in order. You will see that there is a scenario like this, that there is an instruction that has already left the pipeline, and because of that, because it has actually written into what we call an architectural state, which means that it has been written to either the register file or the PC or the memory, there's no way that we can like backtrack this instruction and kind of fix it, right? So and then this is the problem that is unique to out of order execution. In order processor, we didn't have that issue because we always, finish instructions one by one. But now because of the out of order, now things are happening out of order, obviously, right? So we need to figure out a way to kind of like fix this issue for this instruction, right? And for that, we introduced the concept of retiring. So we kind of like, before we said that, things can finish, and finish was equal to being complete. But what we're saying now is that complete and finishing are not the same thing. So the finish thing that we referred to before, the write back stage, is now the retire stage for us. And we have another stage before that, which we call complete, which essentially we say that, whenever our backend machine, which was the out of order part of our design, finish execution of one instruction, go and put it into some form of like a temporary buffer area, and then leave it there until some conditions are met, and then release them. Okay, so it's kind of like waiting area. Think about it as a waiting area for these instructions that are kind of completed, but they're not really clear to be retired. Right? So that's the whole idea of the retirement. And for retirement, we said that basically we will have this structure called an ROB, or reorder buffer, to kind of like have that kind of like a waiting area, that's kind of buffer. The ROB is a circular buffer, which essentially you just keep writing things to it. Of course, this is a limited amount of storage for reorder buffer, which means that if the reorder buffer gets full, then you need to stall the processor and wait for problematic instruction to come back, and then allows your pipeline to go forward. We'll talk about that maybe in the next lecture. But for now, we can assume that reorder buffer can basically house all the instructions that we want. The criteria for retiring the instruction is that all the instructions before that are retired. Somebody pointed out that this basically gets into the same thing, but to be more accurate, we should say that this when all the previous instructions are retired, then it's safe to retire this instruction. Okay. In order to do that, we introduced the notion of head of the ROB, which is basically a pointer. Think about it as a separate register that's kind of like, keep track of where is the last instruction that has been retired. For example, in this case, if the last instruction is the same, is the previous instruction, then the head of the ROB is actually pointing to my instruction. So in this case, for example, it's safe to kind of like retire I1 and move on to the next instruction. But for example, when we retire that, we obviously have to move the head of the ROB down. And what happens is that there might be some other instructions that kind of waiting for to be retired. But since this instruction haven't arrived, since the head of the ROB hasn't arrived yet, I'm not clear to let the other instructions go, right? So I3, I4, I6, and whatever else that exists in this queue, they all have to wait for I2 to comes in, and then once the I2 comes in, then they can retire. The reason for that is that if I2 becomes the instruction that needs to be flushed, for example, if I2 is a branch instruction, then all we need to do is just discard the entire thing in our ROB. So our flushing is as simple as, we just get rid of all the instructions in my ROB and that's it, right? So that's the main reason that we're not letting other instruction go. But if we had let, I3 to be retired, then what would have happened is then there was no way for backtracking I3, right? So that's the reason that we have this retire idea, okay? We talked about like what we will store in ROB. Hopefully, if you have time at the end of this lecture, I'm going to give you one example, and we're going to talk about the details in our processor. But this is something that is hardware specific. So one hardware might save some other things than the other hardware might not. Okay. And then this would be our data path basically. Where instead of like having these lines here originally, which was like, the write back stage for RD, now we are like, sending everything to our ROB, and ROB is the one that is responsible to updating things for us, right? So that's where we kind of stopped in the video. Does anybody have any question for this? So the question is, what is the reason that the ROB has to be circular? Because at some point we're going to reach to the end of the ROB, and we need to go back and continue, right? So basically, I mean, the ROB itself is an array, simple as that. The head of the ROB is kind of like wrap around. When it's reached to the end, goes back up. So that's why it's kind of like a circle. At the beginning, yeah. Yeah, so the question is that if we have a misprediction, do we flush everything in the ROB except that instruction that is actually branch? Yes. So basically, the branch hasn't arrived to that. So if you remember, for example, we resolved the branch outcome earlier in our pipeline, right? So the branch hasn't arrived to the retirement stage yet, but we know that we made a mistake. So what we do is that we get that signal that, we made a misprediction. So that signal goes into the ROB, and ROB, what it does is invalidating everything in the queue, right? So invalidating everything is that, whatever we did after this, they're just completely incorrect. Get rid of all of those. And then we let the branch continue, and then we insert the bubbles and all those things. Does that make sense? Yeah.
So let's say the head of ROB is location that's empty.
Mm-hmm.
And we keep filling up the ROB until we loop back and
Mm-hmm.
reach the same location.
Mm-hmm.
How can we avoid writing into that empty location?
So the question is, let's say that the head of the ROB is pointing to a location, a cell that is not arrived yet. And then there's a whole bunch of other instructions that comes after, and then start, filling the ROB and wrap around and filling all the way. How should we prevent the instructions to keep, overwriting each other, right? So that's a simple thing. So basically, whenever we want to write to the ROB, we'll just check that where is the head of the ROB, and you never actually reach to that point. Because so you basically can think about the way that we're going to write into our ROB is that we have a pointer that is kind of like, head of the ROB. And then we have another pointer that's kind of points to the first available location. So for example, here, right? And then all you need to do is really checking these two indices and make sure that these two indices are not colliding each other, right? So it can wrap around. So this one can go like down, down, and at some point it's going to go wrap around here, here. At some point it's going to point to here, and that's where you're not going to allow to write it, and you're going to stall your processor at that point. So by stalling the processor, basically what you mean is that don't fill the pipeline anymore. We need to wait for this instruction here to arrive. Once this arrives, then we can retire a whole bunch of instructions one by one. I actually said that you cannot retire all at the same time, because that's also a limitation, because you want to write it back. So depending on, for example, how many writes ports you have, you can only write back at you can retire at that many instructions. So usually the same number of lanes that you have, the same number of instructions you retire. So you retire only 2 at a time, which means that your processor also kind of like feed your pipeline 2 at a time afterwards. Does that make sense? Okay, so now let's talk about these two other things. Let's start with this one. Let's talk about like how do we fix the hazards and whether it's going to be new hazards or not. So let's start with an example. Let's say we have a sequence of instruction like this in add, and that's like add x1 x3 that writes the result to x2, and then sometime later we're going to use x2 and write the results to x4. We said that this is basically a raw data hazard, right? So what we need to do is either do the forwarding or stalling or something like that, right? That was our solution for this. For out-of-order execution, if you, for example, change the ordering of this, and if you run sub after add, sub before add, you will still have the same issue that we had before, because here this x2 should get the value of this x2 and not the previous x2. So this is indeed a problem that we need to absolutely avoid in our out-of-order execution, right? Because this is a dependency, and we need to fix this dependency. So we're going to talk about how do we fix that dependency later on. But this is kind of like, here we had forwarding. I'm going to talk about what we're going to do in out-of-order very soon. But some form of forwarding happens here as well, okay? The key thing is that you cannot execute this before this anyway, right? You have to kind of like, stall this and execute this. So if you have dependency, there is no way around it in terms of out-of-order execution, right? So for now, don't worry about this. What I want to talk about is these other cases. So this, we call it true dependency or raw data hazard, right? But let's talk about the other two that becomes problematic in out of order, but they weren't in order. The first one is write after write. So a scenario like this that we have, that you have something written to x2, and then some later instruction you have another thing that is written to x2, right? That's actually, I think in your quiz you also had that, and we said that this is basically not a true dependency. You don't care. As long as you first execute this and then execute this, you're good to go. You don't need to be doing any forwarding. You need to be worried about anything. You don't need to install the processor and so on, right? And we call that output dependence. And we said that these are what we call false dependencies. They're not indeed a dependency. But the interesting happens when we are looking at it at the out-of-order execution scenario, where potentially you might run this before this. So you might have an execution that looks like this. So in this case, this is actually an error. That is a problem in out of order, because if we execute this before this, then at this point, at the end of this sequence, what we're gonna get is, for x2, we're gonna get the value that's coming from the add. But in this case, we are getting the value that is coming from the sub. And these two are not the same necessarily, right? So depending on how do we execute this sequence of instruction, we might get a different result. And that's not what we want, because we want to know beforehand exactly what should be the output of this. And the correct output is actually indeed this, because as I said before, the programmer always assume that the sequence of instruction is what the hardware actually executing, right? So it never thinks that, oh, there might be a scenario that like this sub goes after this add and so on. It always thinks that, okay, if I write a program, my program starts from the very first instruction, goes one by one, and ends in the last instruction, okay? So we have to be faithful to that assumption. So this is true and this is not true. So what it means is that we cannot also reorder these two things. We have to be very, very careful if we have things like output dependency, and we need to fix that, which means that there's an additional problem in out-of-order, additional complexity in out-of-order, okay? But we're going to show how we fix that too. And then finally, there's going to be a write after read, very similar to write after write. We said that this is again a false dependency, because you're reading something and you're writing to it. As long as this happens before this one, we are good to go. But again, for out of order, unfortunately, what might happen is that we first do this and then do this. And since we are updating the value of x2 here, we might read an incorrect value for x2 here. And that's another problem that we have. And we call that anti-dependency, or again, it's a category of false dependency, okay? So the interesting about these two later scenarios is that these two could be easily resolved if we had used another register instead of x2. So in either of these two, if we had used a different register, for example, if we use x5 here, then we could have easily, get rid of this issue. Because, if you had like, sub x5, x3, x4, then it doesn't matter whether you are doing the add first or the sub first. Each instruction is completely independent of the other instruction, and you're writing the results into a completely different register. So this is basically seems to be just a variable issue. So if you're just, limit yourself to a very small number of registers, then problems like this might happen. Whereas if you had, like, for example, infinite number of registers, you could have just easily used other registers. But you might ask why for raw data hazard that's not the case, because remember, we are using x2, which is actually the results of this instruction. So it's not like, oh, if I change this x2 to x5, then the problem is gone, because no, you want this value and you want to do something based on that value, right? So for example, you have something like, x is equal to like, y plus 5, and then you're going to do if x is something, and then do this, right? So you're waiting for this value of x here, right? And this is exactly the same scenario. You're using that value. But what these two are saying is that, so whatever this value is, later on, you want to just replace it with some other value. So why are you using the same register in the first place if you want to replace it? Question. The question is, whose job is it to swap this? And that's actually the part that we're going to add to our out-of-order execution. So the hardware's job is to replace it. Okay? So basically what this means is that, if they're truly independent, so let's actually make them independent. So just let's try to find a way that what we call, renaming in some sense. Let's rename these, like, independent instructions and use other registers for it. And if we do that, we are good to go. We don't have any dependencies for it. We still have dependency for this, and we're going to talk about how do we fix it. But for these two, we don't have any dependency as long as we just rename it correctly. Okay? So the idea of renaming is basically this, that we want to go through our instructions, and with some algorithm that I'm going to describe in the next slide, we're going to change those those registers that we probably going to be problematic. That's going to be independent from each other, just happen to use the same name. So we're going to just rename it. And in order to do that, we use this important trick that, hardware, the number of registers available in the hardware does not necessarily is the same thing that we see in the assembly code. So in our assembly, when we were designing our ISA for RISC-V, for example, we said that we're going to have 32 registers, right? X0 to X31. We only have these 32 registers. We cannot like move on to 64 registers and so on, because if you do, then we need to change our, our instructions. We need to change the bits and all those things, right? But the interesting thing is that, you have this, you have this hardware, and nothing prevents you from having more and more registers if you want to. So for example, you can have 128 registers and so on. But if you only use 32 of them, then it doesn't make sense to have more registers, right? So what you did, for example, implementing your project one was like inside your simulator, inside your hardware, you also use exactly 32 registers. There's like a one-to-one mapping between your registers and what you see in your ISA. But in reality, what we can do is that we can define those X0 to X31 architectural registers. And then you can have much more registers in the hardware and call that a physical registers. And what all you need to do is having some form of a mapping between your architectural registers and your physical registers using the techniques that I'm going to describe. And this not only fixes the issue of the renaming, but also gives you much more registers to play with, okay? So basically, this is kind of like, fix this issue here that the first X2 can be mapped into one physical register, let's say P1, and this second X2 can be mapped to another physical register, let's call it P2. So essentially, same architectural register can be mapped into multiple physical registers, and this way we are fixing the issue of anti-dependence and output dependence. Question? The question is that why registers are so expensive in first place? Registers are generally expensive anyway. The problem is in your ISA, you can assume certain number of registers, and the limiting factor there is your output has to, your instruction has to stay 32. For example, from 30 to 64, then instead of 5-bit, you need 6-bit. You need 6-bit for RD, you need 6-bit for RS1, you need 6-bit for RS2, which means that you need 3-bit more, and then that 3-bit should come from somewhere. So you probably down your func3 or func7 and so on and so forth, right? So that's why you need to kind of like, limit yourself there, unless you want to like, switch to 64-bit instruction and then, change things. But on the physical side, if you kind of like, say, okay, my X2, sometimes it's P1, sometimes it's P2, sometimes it's P3, and then having this indirect, translation that I'm going to describe, then you don't need to change your ISA at all. All you need to do is just changing your number of physical registers. Yeah, the question is it similar to virtual address and physical address? Yes, it is. In some case, yes. So we're actually going to get to for the virtual address, and we're going to describe that to you too. Yeah, but that's actually the opposite of this. So in virtual space, you have many more addresses. In physical address, you have less. In this case, you have less in virtual and more in physical, but same concept. Question? So the question is, where are these physical registers located? So our register file indeed is, we call it physical register file, and then you store those in your physical register file. So when you're implementing, so for example, in your project, think about yourself like implementing 32 of that array, you do 128 of those. And then you have some mechanism that whenever you see X0, for example, sometimes you assign it to P0, sometimes you assign it to P1 and P2 and so on. There is an algorithm obviously for it that we're going to describe. But that's the idea. So there is a level of translation between your instructions to the actual usage of hardware. Good. All right. So how do we do that? We do the renaming using this table called RAT, register alias table. And what it does is that there is one entry per each architectural registers. And again, architectural registers are our X0, X1, X2, and so on. Physical registers, we usually show it with P, so P0, P1, P2. And let's assume that, for example, we still have 32 architectural registers, but let's say we can have much more physical, registers, maybe 128 or so on and so forth. Okay. So what we're gonna do is that we're gonna, for every instruction, we want to rename this instruction set. Okay. What we're gonna do is that for the destination, since we're gonna write something to that register, we're gonna rename it and we're gonna assign a new register for it. For our sources, we always keep the previous register, previous physical registers. Okay. Let me go through an example, and you will understand it better. So I'm going to then go back and talk, show this algorithm one more time, so you get the idea. So let's start with the simpler example. Let's say we have only 5 architectural registers, X1 to X5, and then we have 10 physical registers, P0 to P9. Okay. What we're going to have is we're going to have this RAT table, which essentially what this RAT does is that for every single architectural register, there is an entry. Okay. So there is an AREG to P map or PREG mapping. Okay. So in front of each of these architectural registers, we're going to write a physical register. And then we have another table called free pool, which, since we have more physical registers than architectural registers, there are some physical registers that are we call free, which means they haven't been assigned to anything. We're going to keep track of them in this second table here. Okay. So let's start with like some initial mapping. Let's start with something simple. Let's say that we have X1 map to P1, X2 to P2, X5 to P5, and so on. And as a result, my P6, 7 to 10 are free at this moment. They haven't been assigned to anything. Okay. So this is the initial mapping. Now let's say we have this sequence of 4 instructions, and we want to rename this using our renaming strategy, using that algorithm that I told you. Okay, let's start with the first one. So what we're going to do is that we're going to just look at this instruction. Just forget about all these other instructions. What we're going to do is that for our source registers, we're going to look at the table, and you're going to just take whatever register that is assigned to, and then we're going to just put it there. Okay. So what we're going to do is that we're going to say this is an OR instruction, and X1 is mapped to P1. I'm going to write P1 here. And X2 is mapped to P2, so I'm going to write P2 here. Okay, so far so good. I'm just going to go and look what is the mapping between them, and I'm going to put it into my new assembly. The interesting thing happens when we have a destination register. And as I said, for destination register, what we're going to do is that we're going to change this mapping to another mapping. The reason for that is we want to rename our destination register. We want to assign a new register every time that we are writing to it, to avoid the write after write and write after read data hazard. So what I'm going to do here is that I'm going to go to X3, and I'm seeing that X3 was assigned to P3. So I want to change that. So what I do is that I'm going to go through my free pool, and I'm going to pick the first register that is free, that is available. I'm going to pick that, and I'm going to replace P3 with P6. Okay. And what I'm going to do is that I'm also writing that P6 as the new destination register for me. Okay. And also we'll keep track of this P3 for some other reasons that I'm going to describe later. But what happens after this is that now P6 has been removed from my free pool. And you see P6 here. I haven't released P3 for some reason that I'm going to describe later. So still P3 is occupied for reasons I'm going to describe later. But P6 is no longer in my free pool table. All right, so this is the first instruction. X1 and X2 are P1 and P2 now. and X3 has been changed from P3 to P6, and this is the new mapping. Is that clear so far? Any questions? Okay. Yeah. So the question is why we didn't use P3. Think about that scenario where we had sub writing to X2, and then we had an add that is also written to X2. We want to eliminate those scenarios. So what we are saying is that whenever something is being written to this register, I'm going to just use a new register. So if I change this to, for example, P5, and then if I change this to P7, it is guaranteed that these two now are going to use the same. So whenever I'm writing to something, I'm going to just use a new register. So that's my strategy. This way, I'm guaranteed that I'm going to, like, eliminate those cases. So the question is, at the end of the program, how do you know which value, which physical value register to use? You still have this mapping here, right? So for example, if you want to, output A0, which is your X10, for example, you go into that table and see what X10 is pointing to. For example, it's pointing to P57 or whatever number is. You output that, if that makes sense. So the question is, the value of that table, if you're executing out of order, may not be the most recent value. Actually, the whole point of renaming is that avoiding those situations. So as I'll finish this, you will see that it's actually not going to be a scenario like that. Unless you have a raw data hazard, in that case, you need to do something else that we will. Okay. So let's continue with our renaming. So we kind of finished the first part. Let's go into the second instruction here, this add instruction. Again, I have to first look at X4 and X3. And the interesting thing that happens here is that, so X4 obviously is assigned to P4, but now you need to use P6 for X3, because now you have already updated that value. Okay, so you put P6 here instead of putting P3. If you didn't do that, then you will have a problem of write after read and read after write. Okay, so we're gonna put P6 here, and for X4, now what I need to do is going to that table, find the first free register, replace it with with P4. Okay, so that's what I'm going to do. So I'm going to replace this with P4, and remember, you don't change this to P7. This is still P4, but this one is P7. Okay, so that's might be confusing to you, but that's the source register that's coming from previous instructions. But this P7 is the destination register that's coming using for future instructions. Okay. And that's the actual interesting part of this out of order execution, because now if you look at, for example, the next instruction, when we start doing the renaming for this one, so renaming should be easy. For X2 we use P2, for X5 we use P5, and for X3 the previous value was P6, and now we are changing it to P8. Okay. And then you see that in original instruction set, we had OR X writing to X3, and we have sub writing to X3. But now I have OR written to P6, and now I have sub written to P8. And now I'm free to actually move these things around, because these two are not independent to each other anymore, right? So that's the main reason that we are doing the renaming for our system. Yeah.
After the OR.
So the question is, are we assuming that the add instruction happens after OR? And that's a problem that we need to solve with kind of like a raw data hazard in some sense, because we are reading after write, and that's still a raw data hazard that we need to be worried about. So that's a separate problem that renaming doesn't help us with that. That's a separate mechanism needed for this. Do we keep the physical register in stack somewhere? When we are so the question is, when we are using X3, what happens to P3, right? So here we still haven't, remember, we haven't freed P3 yet, okay? And I'm going to talk about what will happen to P3 when we are freeing P3, because at some point this P3 has to go back here, right? It has to go back to this table. I still haven't talked about that. For now, just assume that P3 stays unwritten, in the sense that whatever value that I write before this, that's the value P3 has, and nothing changed for that. Okay, because all these registers are still in my register file, so they are safe. Nobody's written anything to them. We're just adding this to additional data structure to our hardware. Okay, it's just a simple mapping. Okay, and then finally, last instruction. This is an immediate instruction. For immediates, we also do renaming. Of course, this 2 doesn't need to be renamed because this is an immediate, so there is no problem with that. What you need to rename is X3 and X1. So X3 has to be P8 now. So remember, this here was P6, but now it's P8. And X1 has to be renamed. So now X1 is P9. So we put P9 here, and 2 is just an immediate. It has nothing to do with the register, so you just put 2 there, okay? And the source of confusion for many people is for like load and stores and all those things. So again, the rule is, if you have a source register, whether that is store or load or add or whatever it is, you go to your RAT and you just write that register in front of that instruction. If it's a destination register, like load, you have to rename that number, that register number, to something else. Okay, so that's the idea. For add for immediates, you don't need to change anything because immediates are not registers, obviously. Okay, so is that clear, or any questions about the renaming logic? Okay. So now the question of when to free, which means that, for example, looking at this, originally we had P3, then we changed P3 to P6, then we changed P6 to P8. And then at some point, all these registers will be used, right? So we need some mechanism to kind of recycle those registers that we no longer in use and put it back into our free table. And that part is not trivial. We need to be careful of when to free. And the answer to when to free is when the previous instruction is in complete state, not the retire stage, because for retire we need to wait a long time. But once it's in complete stage, we can free the previous instruction. Okay. So for example, let me give you an example. Remember, we had this OR instruction, and originally X3 was assigned to P3. So when this instruction goes into the complete stage, when this OR instruction goes into the complete stage, then we can retire the old value, which is the P3, not P6. We let the P3 to becomes free. The reason for that is, if you actually play with some different instruction, you will see what happens there. But basically what happens is that if you have scenarios where you need to flush, if this hasn't been completed and hasn't been written into my ROB, then I will lose that data if we decide to flush. So we are basically avoiding a scenario where we suddenly decide to flush and we don't want to lose that old data. Okay, so the rule is, I'm going to free this whenever this new instruction gets into the complete stage, because at that point I'm going to store that into my ROB, and then we are good to go. If not, something needs to be recovered, I can just go to my ROB and recover that value. Okay. So basically, in this case, we still just showing the renaming logic. But if we had shown the rest of the pipeline, there will be some stage that this OR goes into the complete stage. And then at that point, we're going to add this X3 to our free pool. If this, for example, this instruction happens to reach to the complete stage before this instruction start being renamed, then, for example, we could have used P3, sorry, this P, P3, for example, instead of P9, okay? So it's just about the timing, and the hardware knows these things. So we will show you the actual logic for it. But generally, the idea is we free instructions, we free registers when the instruction reaches to complete, and we don't free P6, we free P3, the old destination register. Okay, is that clear? Any questions? Awesome. So to give you an idea of like what changed in our hardware, basically what we are adding to our pipeline is that previously we had our instruction memory or instruction cache here. It goes to the pipeline, and at this point we were doing the decode, right? So we just whatever this value was, we're just directly going to the register file and grab that value. Now we need to go into our RAT table, our renaming table first, and kind of like, translate this value to whatever it was to a new value, and then access what we now call physical register file instead of just the register file, okay? And at this point, we're gonna get P1, P2, P3, whatever it is, okay? So we are adding additional step in our decode where we do the renaming as well. Does that make sense? So adding ROB and renaming together, that would be our kind of like, our new data path, where we basically the ROB is the one that's kind of like interact with our RATs and interact with our physical registers. It interacts with our RAT to kind of tell when to free. So we said whenever the instruction completes, it's going to return itself into ROB, and the ROB going to send the command to free this register. And that will be going to the RAT. It also, whenever we want to write back, when we want to actually retire the instruction, it sends the actual value to physical register file. That's what the write back was originally in our system. Does that make sense? Any questions? Okay. All right. So we talked about this. We talked about this. Now let's talk about the first part, the tracking part, because that's where we need to fix the raw data hazard, and we also need to kind of like, know which instruction is ready and so on, okay? So we talked about the ROB and renaming as the two main things. Let's talk about this, another thing that we call reservation station or scheduling algorithm, which we basically allow us to send another instruction. Let's have a quick break, maybe for 5 minutes, and then we're going to come back and talk about this. So let's continue. Okay, so let's talk about this part, and let's talk about how do we know which instruction is quote unquote ready, and how to fix the raw data hazard in some sense, okay? So for example, let's say we have an example like this, where we have a bunch of, add and sub instructions, and we have this instruction here, which is dependent to, we have this instruction here, which is dependent to this instruction because of the raw data hazard. So obviously we cannot execute I3 before I1. But we can safely, for example, execute I4 before I1, right? In other words, I4 is ready to be executed versus I3 is not ready because I3 needs to wait for I1 to finish and then goes into the pipeline, right? So we need a mechanism to kind of like, figure these things out. And this has to happen inside the hardware itself, right? So in order to do that, we use this queue called reservation station or RS, which what it does is basically as soon as we read our register file and decode our instruction and create our control signals and so on, we're gonna put each instruction that we read into one line, one row of this reservation station. And then we're going to use a mechanism in this reservation station to kind of go through these and check the source and destination registers and see if both the source registers are available. Then it's going to just feed it and put it into our execution stage. Okay. So the trick that we're going to use is that for every instruction that we read, we're going to read all of these 4 instructions and even more of that before and after. And each one goes into one line of this reservation station. And what this reservation station, this logic within the reservation station do is it's going to check that whether these 2 source files are available or not. And by notion of available is that we need to kind of track that whether there's another register that's kind of like one of these registers are being already written into my pipeline or not. If it is, then this one can't go inside. If it's not, then this one can go inside, right? So that's the trick that we're going to use in our reservation station. And then another thing that we're going to couple with our reservation station is that now instead of like having one stage for our execution and the other stage for our memory, we're going to combine these 2 and call one unified thing called functional unit. And what we're going to do is that instead of like saying that, oh, all the executions has to happen in one cycle, memory has to happen in one cycle and so on, we're going to say that basically this is a field that we're going to, once we put things in the reservation station and we want to kind of what we call fire them, we just put them into our functional units and we're going to let them to finish whenever they want to finish. And once they finish, they're going to just go and write themselves into the ROB. So we kind of basically kind of like make ourselves independent of how long does it take for one instruction to finish, because we have multiple lanes, right? Remember, we have multiple ALUs, we might have multiple ports to the memory and so on and so forth. So what the reservation station does is looking at this port, this lane, let's see which one is available. It's going to put one of these instructions into that lane, and it's going to move on to the next instruction. We don't care what happens inside. It's going to take a while for those instructions to finish. For example, if it's an add instruction, it might take in 1 cycle. If it's a multiply instruction, it might take 3 cycles. If it's a load instruction, it may take 100 cycles. We don't care. We just know that which of these lanes are occupied. And then whenever they finish, they're going to write themselves into the ROB. And we just can move on with our life, right? So that's the idea of we're going to have what we call multiple FUs. The name is not the best name, but we basically, do FU and then just, send the instruction inside. So this would be basically our design, where we're going to have functional units, multiple of functional units, because remember, we have a superscalar processor now. And the reservation station basically sees the source registers that are available and the operation that needs to be done, and look at these functional units, see which one is available, and then just assign that instruction into that functional unit, and then just remove it from the reservation station in some sense, okay? And once these are finished, they're going to go and write themselves into the ROB. So we basically kind of like have 2 checkpoints at the beginning and end. This is our reservation station. This is an ROB. In reality, these 2 might be the same thing, similar to the way that we describe our instruction memory and data memory. They could be the same hardware, just different part of the same hardware. But usually what we go with in this class is we are assuming that reservation station and our ROB are 2 separate logic, okay? So two queues, write things to it, and then move on. One thing to keep in mind is that this, within our functional units, we might have pipeline stages as well, because you don't want your functional unit to take only 1 cycle. You can now afford to have multiple cycles for your functional unit, because, for example, you can now have a floating point multiply. You might have a floating point division. You might have, I don't know, a complex add and compare or whatever you want to do. So you can do things at multiple cycles now, but there could be some instructions that only takes 1 cycle, like a simple add or simple multiply and so on. Okay. So this basically is kind of like, our updated design in some sense, where we have our fetch, decode, rename. Then we put it into our reservation station. Then we're gonna execute that, which we usually call fire. Then that execution can happen out of order. Then it's gonna get completed. You're gonna park themselves into this ROV, and when it's time for them to finish them, to let them go, we're gonna retire them and let them go. Okay, so that would be our kind of like a timeline for our instruction. Question. So the question is that in this case that we have like, different lanes, that this one, for example, takes 1 cycle, but this one takes like, I don't know, 10 cycles. Next time that we want to, excuse me, fire something, should we wait for this 10 one to finish, or can we wait for this first one? So what it does is that these lanes are independent from each other. As soon as they finish, they're going to make themselves available. So think about like all of them have a 1 bit of availability, like 1 at the beginning, all of them are 1. 1, 1, 1, 1. Then we issue this, we fire this instruction, and maybe this one becomes 0 and this one becomes 0. This one after 1 cycle becomes 1 again, but this one takes like 10 cycles to become 1. So the reservation station sees this, and then the next instruction that wants to fire, it will just go and fire it into this. So this one becomes 0. So basically, again, the whole idea is that decouple these lanes from each other, so that then you can schedule multiple instructions independently from each other. Does that make sense? So the question is, what is the clock cycle? Still, your clock cycle is the longest among all these stages. What I'm saying is now I'm telling you that your previous execution stage is now multiple states, multiple clock cycles. So you don't add in 1 cycle, you maybe do partial add in 1 cycle and the other. I'm basically breaking down the critical path within my execution, if that is the critical. Still, your clock cycle is defined as the maximum of all these things. So these are usually has to be obviously kind of equally spaced, otherwise it doesn't make sense. So the whole premise of how do you select your cycle time is the same thing. You just find the critical path, 1 over that should be your frequency. But we are basically breaking down to much smaller. As I said, like, modern processors have 20 ish pipeline stages because of these techniques like that I'm showing here.
Wouldn't that like not be able to send data address at all? Because you're already showing the instructions before you're putting it in the reservation.
Good question. So the question is, why are we doing the reservation station after reading the register file, basically, right? Because if there is a data hazard, for example, if forwarding is needed, we already read this instruction incorrectly and we're putting incorrect things into our reservation station, right? And that's the trick that we're going to use. So instead of forwarding, what we're going to do is that we're going to show you that basically when we are writing things in our ROB, the ROB is going to go and update my reservation station. So once I have that dependencies, once I need forwarding and those things, all I need to do is a mechanism from ROB to reservation station to update these things. Does that make sense? All right. So what is inside the reservation station? There are multiple things that we need to store within our reservation stations. We need to, first of all, show that whether this reservation station is being used or not, which means that whether they are available for a new instruction. Same as the ROB, if the reservation station gets full, you need to stall the processor. You need no longer fetch new instruction. Let these things clear out and then start fetching things. But that's rarely happens because you usually, execution is basically the bottleneck in your system. So that rarely happens, but it might happen that your reservation station gets full. You store your opcode your opcode basically tell which instruction this is, whether it's in add or subtract and so on. You store your destination register, your source register, and the two important things that you store is whether your source registers are ready or not. And that's exactly what you're doing in order to know that whether this is a raw data hazard or whether it's waiting for a previous instruction to be written first. So that's where we're gonna do this trick of keeping track of things and not allowing the raw data hazard. So if you go back to that example that we had a sub and we had an add. And if you want to do the add, for example, writing to X3 and reading from X3, this sub, this X3, this 1-bit value of X3, in this case, would have been equal to 0 because it's not ready. Versus for this one, the sources are ready. So we only execute this after this by using this technique that we are using on reservation station. Okay, so we are fixing our raw data hazard this way. We basically pick the functional unit and the ROB number here as well. Once I'm actually giving you the example in the next slides, you will see how this happens. Okay. So basically, our out-of-order execution steps with that gonna be these things. So we have the same fetch as before, PC plus 4, PC plus 4. And if we have a superscalar processor, we're gonna fetch multiple things at the same time. We're gonna, for example, fetch PC and PC plus 4 at the same time. And then what we call a dispatch, which dispatch in basically it's similar to the way that we were doing the the decoding in some sense. We just put instructions into the reservation station. We read values from the reservation station and from our register file as well. Another important thing that happens during the dispatch when we are actually putting things in our reservation station is that we also reserve an entry into our ROB. So whenever we put something in our reservation station, we say that this thing needs to be finished sometime soon. So I have to reserve a spot in my ROB to make sure that once this instruction is complete, there is an area for this to be stored. That's why we are kind of keep track of our ROB number too. If either of these two or both of them are full, we're not gonna issue a new instruction. We have to stall the processor on the left side. We don't have to fetch and decode. We should let the processor to be cleared, the functional units to be cleared. And then we can issue a dispatch a new instruction. Then we call what we call a issue or fire, which basically is just assigning instructions that are ready into my my functional units. And then with that, we also release it from the reservation station. Once we fire that instruction, we basically put it in our functional units, and we don't need to keep track of it in the reservation station anymore. Then we have a complete, which basically the complete means that I write my results into the ROB. And another very important thing that happens at this stage is that I have to go back to my reservation station and make those registers ready. So I'm going to tell everybody that, remember that I wanted to do add and write the results to X3. Once this action has been completed, I need to inform everybody that X3 is now ready. So now it means that the sub can goes without any issue to the pipeline. So I'm going to go to my reservation station. I'm going to update the value of X3, and I'm going to make X3 ready, and then X3 can move forward. Yeah.
Is there no forwarding now anymore? We're like releasing the dependent instruction once it's complete.
So the question is, there's no concept of forwarding anymore. So basically, this is what the forwarding is, right? Once it's complete, we just put it back into my reservation station. It's still one cycle technically, right? So exact same thing. Still, you do the forwarding. If your functional unit takes only one cycle, this happens within one cycle. So basically, this is like forwarding from M to E. Here we are forwarding from complete to issue or to fire in some sense. It's still one cycle if it takes one cycle. If it takes more than one cycle, so it's like a load use scenario. You have to stall for that many cycles before you can forward. So the question is, how many instructions do we put into our reservation station at every cycles? That many that you have in your superscalar. So everything is with the number of n. So if you have 2, you put 2 at the same time, and you retire 2, and you do everything by 2. So the question is, superscalar is the functional unit? No, superscalar is exactly this. So when you say we have a 4-issue processor, it means that a 4-issue core, it means that we can issue 4 instructions at the same time. So we're gonna dispatch 4 instructions into my reservation station. I'm gonna retire 4 instructions at the same time. So everything comes at 4. So all these steps that we do, we fetch 4 at the same time, we decode 4 at the same time, we dispatch 4 at the same time, we do everything at 4. So that's kind of the decision that we make at the beginning. Does that make sense? There's still one. So each smaller unit within your functional units is still 1 cycle. But what I'm saying is your multiply can now take multiple cycles, or your load can take multiple cycles. I'm giving you an example for all these stages, so it will be much more clear. Yeah. Yeah. Yeah, so the question is that since basically once it's complete, it has to go back to the to the reservation station to update the RD. How does that work? So I'm not going to go through the details of that, but typically the way it works is that it's broadcasting. So it's going to say that I'm making, for example, P3 ready. And it's going to broadcast it to all the lanes, and all the lanes going to listen to that broadcast, and then going to take it. So basically, it's not like when we go to 1 by 1, we're just going to say the P3 is being updated, and everybody think about like every line is just one person that kind of listen to this broadcast, and they're going to update themselves. We're not going to talk about the actual hardware for it because it's a little bit complicated, but it's kind of like that. So the question is, if you have a write, and read, remember the first 2 writes are removed because of renaming. So you have write to one register, write to another register, completely independent from the first register, and the read is whatever whatever the dependency that it has. So you don't have write, read. You always only had write, read, because writes is already removed because of renaming. All right. So let's actually go through one pretty complicated example that kind of goes through all these things that we talk about. And by the end of this example, hopefully we have a very good understanding of how all these things work. So here I'm showing all the tables that we discussed. So this is my ROB. This is my RAT. This is my free pool. This is basically just keeping track of readiness of each register. So basically, still I'm having 10 physical registers here. So I have 10 entries that basically is 0 or 1. And this is my reservation station. Okay. So I'm assuming that we have 5 architectural register and 10 physical registers. Okay. And then now let's start with these 4 instructions, and then see what happens at every single stage of my pipeline when we are doing the renaming and fetching and dispatching and so on and so forth. Okay. And the way I'm going to show it to you is that I'm going to show C some number, and C is the clock, and the number is the cycle that we are at. Okay. So right now we are at cycle 0. And the first thing we need to do is fetching instructions. And remember, this is pipeline processor. So many things happen at the same. So it's not like we're just fetching. We fetch some instructions at the same time. We are decoding some other instructions, and we're renaming some other instructions, and so on. So we need to show multiple things at the same time. Okay. So let's start. So we first fetch two instructions, these two instructions, right? And once we fetch that, it basically we go to the instruction read PC instruction memory and put it into our pipeline registers between fetch and decode. Same story that we had before. So nothing happens to these tables that we had. It's just basically we are writing things from fetch to decode, same way that we had for pipeline registers. So nothing interesting happening from that. Question. Yeah, so the question is this, assume n is equal to 2. Yes, that's good. Yeah, 2-issue processor. Okay, so I fetch these two. Now I'm going to cycle 1, and I need to do two things. I need to fetch new instructions, and I also need to decode those two instructions that are read, right? Again, the decode part, nothing interesting happens. It just goes inside my controller. We check the output and all those things that we extensively discussed so far. Again, nothing in terms of these tables. We also do PC plus 8 in this case because we are 2-issue, so we need to jump by 8. And we do PC plus 8, and we're gonna fetch these two other instructions. Okay, so these two instructions are also gonna be fetched, and now we are jumping into cycle 2. So for now, nothing has happened. Pay attention to the default value of all these things. So first of all, our register are all yes, which means that all of them are ready because nothing has been written to them. So all of them are Y or yes or ready. You can use it with Y. Another thing that we have also another table for our functional units. For now, I'm assuming that I have 3 functional units. One of them is ALU. The other one is also ALU, but this ALU also is able to do the multiply for me. And then we also have the memory stage, basically as another functional unit. So I have 3 functional units. 2 of them are exactly similar. Just one of them is capable of doing multiply. The other one is not. And I have a memory functional unit too. And again, these 3 functional units are also ready because nothing has been used so far. Okay. Any questions so far? So what I mean by, so the question is, what do I mean by memory as a functional unit? So the trick that I'm using is that I basically say that if I want to do something with my memory, for example, load or store, I'm gonna treat that as a functional unit as well. So I'm gonna say that this is another functional unit. So whenever I want to fire something, if it's a load, I'm gonna just put it into the functional unit that is relevant to my load. So I have a small adder that do the RS1 plus immediate to generate the address, and then that issues the request to the memory, and that might take a lot of cycles to come back and so on. So that's one functional unit for me. Okay. Okay, so we are at this point here. So now things start to happen for us. So we fetch and decode in C1. Now we move to C2. At C2, we need to do 2 things. We need to decode these 2 instructions here. We need to decode these 2. And then now we need to rename the first 2. Remember, the first step after decode is rename. And I'm not showing the additional instructions here to just make things simpler, but there will be a fetch state as well here to fetch the next 2 instructions and so on. But I'm just showing a snapshot of the processor, only these 4 instructions, okay? So what should we do for the rename? We already talked about like how the rename works. So basically what happens is this X1 is my source. This X2 is my destination, right? Remember for old days when we were talking about pipeline processors, destination and source. And this was source and this was destination. So I have to rename this. For this X1, I have to go to this table and see what is X1. And I'm gonna basically put that P1 here. This 0 is the immediate, so I don't need to change it. And this this X2 is the destination register. So I need to change from 2 to a new free pool, which is P6. So I'm going to put P6 here. and I'm going to keep track of my old physical register, which is P2. Okay. So I put 2 in the parentheses, which is old, in 6, which is the new one. I put it there. Okay. And then at the same time, since this is a 2-issue processor, 2 things happen at the same time, exactly at the same time. To make things simpler, I'm assuming this happens first and this happens next, but it's equally possible that the other way around, doesn't matter. So for this one, what I'm going to do is I'm going to say that, you know, x2, since this happens before this, and actually this indeed should happen before this, x2 should now get the new value, which is p6, right? Because this is a new mapping between x2 and p. x3 is going to get p3. And now, since this x4 is my new destination register, I need to change that to a new physical register. So as you can see, P6 and P7 are gone from my free pool. And after this renaming, I'm going to get this new way of renaming. So I'm basically have P1, P6, P6, P3, P7. Does that make sense so far? Okay. So that's the first thing that happens. The renaming is going to stop at this point, and I'm going to also decode these 2 instructions. Again, these 2 goes into my controller. You know, control signals will be created, and all those things that we already discussed. Any question at this point? All right. So now let's go to cycle 3. In cycle 3, we need to dispatch the first 2 instructions, which means that we need to put these instructions into my reservation station. And I need to rename the 2 other instructions that used to be in the decode stage. Okay. So let's talk about the dispatch. Dispatch, basically, multiple things happen at the dispatch. At dispatch, we reserve 2 lines in my reservation station and in my ROB. So this is what you see here and here. Here and here. Another thing that happens is that now we need to populate these values into my reservation station. So how do we do that? Remember, these numbers used to be 0, right? And now what I'm going to do is that I'm going to start with the first line that is equal to 0. And I'm going to just put this instruction, this load instruction there, and I'm going to change that use to 1, which means that this line is being in use right now. You cannot overwrite it, okay? Same story for the add. I'm going to just put it there. I'm going to store the opcode of those instructions. This is load and this is add. Then I'm going to go and see what are the destination registers for these, P6 and P7. The source register for this. So this one is P1. And the next one is an immediate. So we just put x0 to make things makes our life simple. So we put 0 here. For this second instruction, P7 is the destination, P3 is the source, and P6 is the other source. Okay. The interesting thing happened here. So when we are reading P1, 0, P3, and P6, we have to read their readiness as well. And as I said, we start from the top because we are assuming that the instruction happens from top to bottom. So we start with this first one first. So we're going to, for P1, we're going to go into this table here and see whether P1 is ready or not. We see yes, so we put yes. 0 is x0, always ready, so we put yes here. And then we look at the destination register P6, and the first immediate thing that we're going to do is that we're going to make P6 not ready. This is very important because we want to write something to this. So one of the key responsibilities of the reservation station is that as soon as it sees a destination register, it's going to go to this table and tell this ready table that, you know what, PC is no longer ready because it's going to be written to, so it's not ready. And the interesting thing that happens is that now if you look at this one, we're going to read P3 and P6, and we're going to go to that table. And since this first happens, and it has to happen first, then for P3, we don't have any issue. We're going to just put yes. But for P6, we just write no to it. So we're going to read no to that. Okay. Same half cycle thing is happening here. Basically, in the first half cycle, we are writing to that readiness table. And then in the second half cycle, we're reading from it. And that's why this works. Yeah. The question is, when are we writing no to P6? As soon as we are populating this reservation station, since P6 is the destination register for this instruction, we have to go to that table and flip it to no. Does that make sense? Okay. And another thing that reservation station needs to do, it needs to fire this instruction in a sense. So it needs to like reserve a functional unit for this instruction. So all it does is that it goes into this readiness table of my FUs and see which one is ready. This load instruction, since it's only memory related, it can only be scheduled into this number 2. So we're going to put number 2 here. And another thing that happens is that for this one, for this add instruction, we can choose either this one or that one. I'm just going to choose this one. So I'm going to use 0 here. So the functional unit that this instruction has to be assigned to is 0 and 2. And as I said, as soon as we populate things in my reservation station, same thing that happens is that we're going to reserve a spot in my ROB. I'm going to start again, similar to the reservation stations. I'm going to start from the top. This ROB has initially starts with all zeros. This is a valid or use. You can call it the same name. And what we do is that once we reserve a spot, then we're going to say that this use is now equal to 1. And we are saving 3 things in our ROB for now. We're going to reserve the destination register, the old destination register, and the PC to just know which instruction this was. So destination register is P6. The old destination register, in order to find this value, we need to go to our RAT and find this value in the parentheses and put it there. The reason that we are keeping track of the old is, remember, when the instruction is complete, we want to free 2, right? So we need to keep track of that so that we know which register to free. And then PC is basically just to know that which instruction this is, so that if you want to know where is the head of the ROB, we use PC to know where the head of the ROB is. Okay. Same story for the second instruction, and that's where we have after the dispatch stage. Is that clear, or any questions? Yes, the question is why, what is old destination register and why we need it? Remember when we were talking about the renaming and we said, when should we free? And we said that we free the old register when the instruction is complete. And that's why. So we basically keep track of old register here, that once that instruction becomes complete, and we're going to talk about the complete stage very soon, then we're going to tell this RAT that this instruction is complete. So go and make 2 free. So I'm going to put back 2 in this free pool. Okay. Does that make sense? So the question is that when P6 is written into P, yes, that's when the value of that instruction is completed. So you no longer need the old value in some sense, because you already have it in your ROB. You just can let it go because ROB keeps track of that. If something bad happens, we can go to my ROB and just read it. So there's no problem. So now I have the correct value of P2. I have correct value of P6 because this instruction is now completed. So I save both of those values, and then it means that now the RAT can safely use P2 again. Okay. You might let me continue, and then you'll probably, maybe it might be clear. Okay. Any other questions? Yeah. So the question is, where is the head of the ROB? That's a good question. It's for now, let's say it's here. Okay. And actually, one thing that I'm not showing is like, finished. I'm going to add that into my table later. Okay. So now let's continue in our cycle 3. Another thing that we needed to do in our cycle 3 was renaming the other 2 instruction. So renaming of this is similar to what we said before. We go and look at x4 and x5 in this table. It's going to be 7 and 5, and we put it there. We change x5 to a new one, so we're going to change 5 to 8, so we put 8 here. Then this is another load, so what we're going to do is, so first of all, x0 same as p0, you don't want to change that. X4 needs to be renamed too, so we're going to change 7 to 9 and put 9 here. Okay, and as you can see, 7 and 8 also removed from my free pool. Okay, so this is the renaming part. Continuing to the cycle 4, now a new things we need to consider, and that's what we call a fire or issue. So when we want to fire, we need to basically look at this this reservation station, and the criteria for firing something is 3 things we need to check. We need to check whether source register is ready, number 1 and number 2. And we need to also check whether the functional unit that this needs to be going to is ready or not. Okay? So looking at these 2, we'll see that for the first one, all 3 things kind of checks. So that's why we fire this instruction, or we call it issue or fire. We issue this instruction. But the second one, it waits for its RS2, so we cannot really fire this. Okay? So what happens at this point is that the issue basically, as soon as we issue this instruction, we're going to just get rid of it from our reservation station. We no longer need to keep track of this in my reservation station. So basically, all I need to do is just change this use back to 0. I don't need to even remove these other things. Once I change this back, later on, it's going to be replaced. Another thing that I'm going to do is that since this is going to be assigned to functional unit number 2, I need to change this readiness of FU2 to 0, because now there is an instruction within this functional unit. As soon as this is finished, I need to put this back as ready. For now, it has to stay no. Okay? So that's basically it with our issue. We got rid of this instruction. We put it into our functional units. We make this functional unit not ready, and that's it. Okay? So now let's talk about the dispatch of this second half. So the dispatch, same story. We read first this instruction. We assign a new value in my reservation station for this one. Same for this one. I'm going to reserve 2 spots in my ROB. For this one, I'm going to put use into equal 1, put OR here, put P8, P5, and P7. Reading P5, I'm going to go into this table and see whether P5 is ready or not. I see yes. Then I'm going to go and see P7 is ready or not. And I see no, because this P7 was being used in the previous instruction. So I put no here. And then immediately, as soon as I see P8, I need to go and change this 8 to no as well. So it was yes, and now I make it no. Okay. Same story for this load instruction. And then, oh, by the way, the last thing I will do is that I put a new FU number for this. Since this is an R-type instruction, I either put 0 or 1. Since last time I put 0, this time I'm going to put 1. And the ROB number is basically, I'm going to reserve an ROB spot here as well. Same story as before. I'm going to just put 2 because it's pointing to this. Okay. Then for the next instruction, this is a load. Destination register is P9. Source register number 1 is 0. Source register number 2 is also 0. This is literally P0 and an immediate. And remember, when we had an immediate, we put P0. Both of them are obviously yes, right? The functional unit for load has to be only 2. And the ROB that is pointing to is this. And then since P9 is the destination register, I go and put no into my readiness of P9 as well. Okay. So that's the story of dispatching this instruction. Any questions? Yes. So the question is, the reason that we put things in ROB like that is because these instructions come in that order. Yes. Remember, we still fetch and decode in order, right? So that's why they go into the ROB. But later in the future, for example, let's say, for example, this instruction for some reason finishes much faster than this instruction, and this instruction. So there is a hole in my ROB, and next time I want to put something, I put that into that hole, right? So I kind of like need to keep track of that. You had another question? Yes. The question is why we have two aliases? Because we have, because we are kind of rich. We can put things into my, yeah. The question is, what do we put functional units when we are dispatching an instruction? Yeah, I mean, to make things simpler, we do that, but you can also do this dynamically because this is a little bit inefficient in the case that your scheduling is not like, directly see things. But for now, to just make things simple, we do that. Yes. Question here. Good. All right. So now we go to cycle 5. In cycle 5, we are assuming that things happen in one cycle, for example, for our R-type instructions, and 2 cycles for our memory instructions. So I'm just going to put it down here. 1 cycle for R-type, 2 cycles for load. Okay, just the assumption that I have. So because there is only 1 cycle for R-type, since we issue the instructions in cycle 4 for this instruction, remember, now this instruction is complete because it only takes 1 cycle to add things, right? So we need to do things for the complete stage. What we're going to do is we are going to put this, look at this, right? And we're going to do 2 things for this instruction. Wait. Okay, so actually 1 cycle for load, 1 cycle for R-type. I'm not doing 2. In your homework, I think we do 2. Anyway, so 1 cycle for, so remember the first instruction for the load. So after 1 cycle is actually finished. Okay, so it means that multiple things happen. First of all, my functional unit is now ready because this activity has been done. So I can issue a new instruction at this cycle if I want to. Okay, for this functional unit. So that's number 1 that happens. The second thing that happens is, since the destination register of that instruction was P6, now P6 is ready. So I'm gonna just put P6 back into ready. This also means that I'm gonna broadcast this number, P6 ready, and everybody in this reservation station gonna get that number and they're gonna update themselves if they see that there is a match. So now this P6 gets the updated value. Okay, that's very important to know. Question you had?
Yeah. For the second one, the ROP, why is the old destination?
Why old? Oh, we have to go back and see. I think it was.
Like 85 and 64.
Oh, okay. So maybe it was a typo. Yeah, we're right. You're right. Okay. Yeah. I'll fix that in my slides. So where were we? Issue, dispatch. Oh, complete. Okay. So we were here. So as I said, this is when we tell everybody that P6 is now updated. So go and update yourself. And what happens is that this value gets updated. And as soon as this value gets updated, this value also becomes yes. So that's a cue to the reservation station. As, by the way, if you want to issue this, now you're clear to issue this. Okay. Another thing that happens is, so we do this, and I'm not showing the other column here, which I should have. And that's basically said that whether this is complete or not. And that's also becomes equal to 1. So everything is equal to 0, except this one that's kind of like, equal to 1. Okay, so that's also another thing that happens in my ROB. All right. So that's the end of my complete at this point. So now let's talk about the issue of that same cycle. Remember, we can issue up to 2 things at the same time. So now we go into my reservation station, and I see I have 3 options. And I'm going to check the RS1, RS2 in the functional units, okay? And remember, now this gets the updated value. So basically, you can think about that complete happens first and then issue. And this is all because of the half cycle thing that's happening. Writes happens first, reads happens second, okay? So now I see that, okay, this instruction that used to be problematic, now it's ready to be issued. I'm going to see a def use 0 and see, okay, this is also ready. So this is one thing that I'm going to issue. I'm going to go to the next one and see that this it says no, so I cannot. And this one also I can issue. So I'm going to issue this one as well. The interesting thing is this one is able to be issued because I changed the functional unit back to yes, right, at the same cycle. Okay, so I'm going to issue these 2 things, and the thing that happened is that now 0 and 2 becomes no, right? And then I'll get rid of these in this from my reservation station too. Okay, that's kind of like the end of the cycle 5. Any question here? Now moving on to cycle 6. Multiple things happen at this point. Now, since there is one instruction that is completed, we can actually retire that instruction. Retirement is basically happening in this case that we're going to get rid of that from our ROB. We're going to free that P2 into my my RAT, right? And then another thing that I do is basically I move down the head of the ROB from here to here. So now the head of the ROB is here. And I'm going to put back this valid bit to 0. Okay. Then we go to the complete. Remember, we had one instruction, actually 2 instructions in the functional units. The first one is now finished, right? So as soon as this finished, we're gonna put this back to yes. We're gonna tell everybody that we have P7, right? So we're gonna put back this readiness to yes, and this P7 gonna be updated as well. The second thing that happens is, where am I? Okay. So again, here I'm kind of like make some confusing assumption, and I'm thinking that okay, what will happen if this second load takes 2 cycles, which means that this second load doesn't get finished at this cycle. Okay. So like I'm assuming that this is not completed at this point. Only this one is completed. Okay. I'm going to describe those assumptions more clearly in their homework, so you will see that which one is which. But for now, let's assume that this load doesn't get completed now. Okay. So now we're moving on to the issue stage, and we still have one instruction remaining into our reservation station, and we need to issue that because now everything is yes, yes, and yes. The problem is that no, there's no problem. This one was yes, and now we change it to no. So we issue this one as well, and we just get rid of this. And we are happy and we move forward. We go to cycle 7. Now we can retire this next instruction. We can get rid of the old P3 because the P3 was here. Well, was it P4? I think it was P4. So anyway, I'll fix that. But we put that into our free pool. And since this is the head of the ROB, we can retire that and can move on, right? And then there's nothing else to issue. There's only things that can be completed. And let's assume that now our load is also comes back because there's 2 cycles that we want. And this OR is only take 1 cycle. So these 2 instructions complete at the same time. So 2 things completed at the same time. So both of these goes back to yes. These also goes back to yes. We update them, but there's nothing to be updated. But generally, we do the same thing as always. Since both of them kind of like, at the head of the ROB, and we can retire 2 things at the same time. At cycle 8, we're going to retire both of them. We're going to feed both of them at the same time. And at this point, we're kind of like, go back to square 1. Everything has been retired. Everything now goes back to ready. All the functional units and registers. The only thing that's changing is that now this mapping is not the same mapping that we started with, right? Which is obvious. And then everything is 0 and everything is 0. Also, my head of the ROB is now pointing to this empty location. Okay. And you can think about that this is like a stream of instructions. So it's not like, at some point it ends. It will just continue coming next instruction and next instruction. Okay. Yeah. So this is like, C9 and so on would be the continuation of this. Okay. So this is it with our out of order execution. We will have an example like this for you also to go through in your homework. And basically, there are lots of moving parts and lots of things that you need to kind of like, keep track of in order to understand what is happening at every cycle. Okay. So this is your final data pass with the functional units, the ROB and your RAT. And there are a bunch of challenges, including how do we do, for example, flushing and all those things. I might actually spend a little bit of time talking about that, but these are like mostly advanced topics that we gonna skip for this class. So this is kind of like, most of the things you need to know about out of order execution. All right. So that's it. Thank you, guys.